And hello, welcome to this video. So this video in this video I want to demonstrate maybe some frequency response in LabView of a simulated system. So what do I mean here? Okay, let's say you have a system. Let's say you have a system here, and you send the input signal in. And this is maybe something experimental or something outside. So if you want to do a frequency response on this, you'll need to take note of the input signal, and then you also need to take note of the output. Okay, both of this needs to be plotted with respect to time, and then you do your FFT on both of them. So that you can get frequency response data. Pardon the writing. But I hope you get what we are trying to do here. So you want to test this kind of a setup here in LabView, and get familiar with some of the stuff, how to do it, especially how to eventually later on export all of this, at least the input versus time and the output versus time, to some CSV file. Okay, and after that you can probably try to use MATLAB to try and sort this out using some of their functions, but as of now I'm just interested in generating a CSV file with input versus time and output versus time. That's all. Okay, yeah, that's what I'm trying to do here. So after that, MATLAB has a fast Fourier transform capabilities to help you analyze the data. Of course, in here you will have some other things as well which you can use to analyze. There's a fast Fourier transform right here in LabView as well. You can use that. If you want to use the MATLAB version, by all means as well. And over here you also have time response VIs and frequency response VIs. Now the only thing with this is that you need a state space model or some kind of you need some sort of a transfer function model. So if you don't know what the transfer function model is, you cannot really use the body plot VIs here very well. Okay, you need a transfer function model and some frequency vector for which you want to plot your body plots, and then and there'll be a phase and magnitude plot done for you using LabView. That's provided you know your frequency, your transfer function. If you don't know your transfer function, you are kind of stuck. You kind of have to do things a little bit more manually. As well, that's it to the best of my knowledge. Okay, so anyway, without further ado, we're going to start first by trying to make some hypothetical experimental system that can transform the input into an output. Okay, it's not going to be based on anything physical, so I'm just setting things up so we can run experiments later. So let's start. Okay, so this is where I kind of left off. I was demonstrating some the control design simulation installation on OpenSUSE, and it ran successfully. So this whole thing is done on OpenSUSE, so that it's nicer to use than Microsoft, in my opinion. It's just less laggy in general. Okay, so let's start by designing some of the inputs. So for the input, usually you like to give a sine wave. Okay, you like to give a sine wave. Okay, so there are multiple ways of getting a sine wave. You can actually just use this sine signal here, or more generically you can use this thing called signal generator, which I like. Reason is because with signal generator you don't just have the capability of using sine waves, you can use lots of other signal inputs as well. Input generator. Okay, so this is your input generator. What can you do with it? Okay, in your signal type, okay, if you double click this, under your signal type, you can go under here you can have a sine wave, square wave, sawtooth wave, and even random. Okay, why are these good? Because these other wave inputs have more than one frequency, so they are superposition of many frequencies, and you can test your frequency response over several frequencies if you use things like square wave or even using noise. You can actually have a Fourier transform of this noise. Okay, you can have a Fourier transform of this noise, and hopefully you will get some sort of a signal. You can actually see which things are inside here, what frequencies are inside here. So with random, it's a little bit harder. If you actually try to okay, never mind. We will not do random. We'll not discuss random. If not, you'll go over time. Okay. So what you can do here is you can select from several kinds of inputs. So the most simple input is sine. Okay. You can actually configure your amplitude here via this dialog box, configuration dialog box, or you can do it using a terminal. So I prefer using terminal so I can wire things in from the outside. Offset also, you can use this dialog box or you can use a terminal. So I always prefer to use terminal so that I can wire things in. So this is where you can control amplitude. This is where you can control offset. So what is offset? Okay, normally your sine wave actually oscillates around 0. If not, you put at 500. Okay. If you put your offset at 500, it will oscillate up and down around 500. So that's what offset is supposed to do. Okay, the frequency you can also wire in via terminal. Offset you can wire in via terminal, and this gives you a great degree of control over what kind of sine wave you are actually putting in. Okay, so classically we like to use sine waves. Sometimes we can use square waves or sawtooth even. If you want to spread out our analysis over several frequencies and get more data points per test. Okay, because those are superpositions of many sine waves. Of course, for nonlinear systems that might not always work. Okay, for linear system it's pretty easy to do this. Okay, so next thing I want to do is to start making a nonlinear system. So how is this nonlinear system supposed to look like? Alright, I'm going to try using an Ahemos relation. Okay, so this is some chemistry thing, it's based on, let's say you have you can vary the if you have this sort of setup. Okay, you have this sort of setup. Okay, you have a reactor, a chemical reactor. Okay, so this is actually going to give off some heat, right? And this heat is going to change temperature, and this temperature is going to affect the reaction rate. Okay, and what's the reaction rate? It is actually proportional to K, which is K times the concentration of reactants. If you have A goes to B reaction, something like that. Okay, so if let's say this is an endothermic reaction. If an endothermic reaction, we are going to have the heat that you actually take away is equals to your reaction rate times delta H, which is the heat of reaction. Okay, and this reaction rate will be correlated directly to this K. And what is K? This is a reaction rate coefficient or constant. Well, it's not really constant. K, you can use Ahemos model. A equals to exponential minus E over RT. Okay, so this is the Ahemos relationship. Okay, and you can see it's a non-linear with respect to temperature because this is an exponential with respect to temperature. Okay, so if you were to supply heat to this reactor, you will obviously increase the reactor temperature. If you were to of course, if your reaction rate increases, then of course the temperature will drop. So there's some sort of negative feedback. So this is kind of the system I want, or maybe probably have something simpler. Okay, so let's do this. Okay. All right. So let's say this is like the heat input. All right, the heat input that you want to give to these reactors. Okay, so heat input. So if you have a reactor, okay, you are going to supply some heat to try and get the reaction going. Okay, so of course here to increase the heat, you can increase fuel flow rate, and of course you have some transfer function. So if you increase if this is a gas heater, you increase the gas flow rate, you're going to increase the heat, and this is going to have some transfer function. So I'll just assume it's linear. Okay, I'll just assume it's linear. So let's give it some flow rate. Okay. All right. So where's the transfer function? Okay. So this is a transfer function, and it's going to take some time to compile, but yeah, I will just call this the instead of a heat input, I'll put fuel input, fuel to heat, heater energy transfer function. So you can replace this with some real values. I'm not going to bother even doing that. Okay. Yeah. What I'll do is I'll just wire this output into here. And the next thing I'll do is to wire this to get some temperature, right? Okay. Okay, so let's see. I'm gonna have another transfer function. So I have a heat energy to temperature, kind of a transfer function. Okay. Yeah, so I guess with OpenSUSE, it may be a little bit slower when you drag items here, but on the whole, Linux system is smoother. But I guess the reason why this happens is because from Linux to sort of Windows commands, there is some compatibility layer kind of thing. Okay, but never mind, just ignore that. Okay, so we'll have heat input to temperature transfer function. Okay, both of these I will assume to be linear, and when you have temperature, what happens? You will have some feedback. Okay, so I will use the utility here called memory to get a temperature feedback. Okay. All right. So so this is what you'll do. You'll have an initial value, which you just can make the constant. And let's reverse the terminals so that you can really see its feedback. Okay. So let me give it arbitrary. You start at 500 Kelvin. So let's put Kelvin, right? Kelvin. So so we'll give this as output, and of course I want to have my indicator of the output. Okay, I'm kind of a bit all over the place, but things will get cleared up once once things goes. Okay, so we have temperature versus time. So to make it intuitive, you use degrees C. So what I'll do is I will just subtract 273. Okay, 273 randomly, and I'll just get this degree C. I'll feed the output here into this because all of this will be in Kelvin. I want it to be in Kelvin. I've not programmed what the transfer function is yet. It will just be this kind of thing. Okay, so heat input to temperature transfer function. I will assume the reactor is adiabatic, so there's no heat loss mechanism. Of course, you can put that in, but that's not the point. Okay, so there's this temperature feedback. Okay, after you get temperature feedback, what do? Okay, I'll use the Ahemos relation. So first thing, I'll need the gas constant. I wonder if the okay, never mind. Maybe not gas constant. Okay, so how have the exponentials things here? See whether I can reverse terminals now. Okay, so what do I need to make my Ahemos relationship? Okay, so I have exponential minus E over RT. Okay, R is 8.314 J per mole per Kelvin. Okay, then let's just put activation energy at 500. Okay, this is a ballpark figure, 50,000 joules per mole. Okay, 50,000 joules per mole will be the activation energy. So this is slightly physical, but yeah, you can kind of change it yourself later. So let's have a constant. We have a constant, okay, 8.314, which will be my R. Yeah. And this will be, let's see how long I have left. This will be maybe 50,000 joules per mole. And let's see. Once I have this, I will need to multiply both of these together, the R and T together. Okay, so everything's sort of backwards, but okay, R and T together will be multiplied, and then I will take the inverse, okay, reciprocal here. Okay, and then what will happen? I will multiply by 50,000. So what am I doing? I'm taking R and T multiplied by together. I'm taking the reciprocal to get 1 over RT. I multiply that by E, and then I'll take the negative. That's what I'm doing. Okay, so I'll need to take the negative, negate. Okay, and then this whole thing will go and become exponent. It will become the exponential thing. So this will actually give exponential E over RT, and I will just assume, for simplicity's sake, I'm not going to put the AE over RT thing here. I'm not going to bother with that. I'll just put exponential E over RT, and that will be my reaction rate, so to speak. Okay, and after that, this will be a positive number. Actually, maybe I should put in case it's too slow. Let's see some typical values. Okay, so if you do some search online, as this chemistry libre text. Okay, typical A value can be like 15. So I'm just going to use 15. Okay, so it's not that far off. Yeah. Okay, I'm going to have 15 here. Let's make a constant. Let's do 15. And then of course, we can actually multiply this together. 15. So we'll get the reaction rate, so to speak. I'm not putting the reactant concentration because that's sort of redundant. Now, this thing, what am I going to do? I'm going to multiply by a heat rate. Okay, how much? So this is in how many moles per dm cube per second, kind of a thing. All right. And then I'm going to multiply by a heat rate. Okay, so I'm not going to sort of do anything here. That's too wild. Okay, the typical okay, heat of reaction, maybe it's a 50,000, again 50,000 joules per mole per Kelvin, or 50,000 joules per mole. Okay, I'm just going to use 50,000, and this will be endothermic, so I'm going to subtract it off, and this will be of course heat is being supplied to the reactor. I'm going to have this heat of my heater. I'm going to minus the endothermic reaction bit, and then I'm going to put this into the temperature input. Okay, now that's basically what we have, and let's give this a simple transfer function. Okay, so I will set this from like 0 to 1, and let's give this thing a heater power of 50,000 also, so that we won't be too far off. Okay, and give this a heater power of 50,000, and we'll give this some time delay, maybe 3 seconds time delay. And then this okay, this heat input to temperature transfer function, I'll just give it a 0.01 gain. Okay, so both of these are first order. And I'm not going to do anything that complicated with them. The complicated part is the nonlinear thing, which we might want. Yeah, frequency response testing may be useful, it may not be useful, but it'll be interesting to see how things pan out. Okay, so I'll put 10 seconds as the process time. 0.01. Maybe 0.001 as the gain. Okay, not too bad. Alright, so this is the system. We may take a while to tweak it, but let's at least put this to the test and see what happens first. Okay, so this is our temperature versus time. Okay, so we'll just tweak it along the way till it sort of looks sensible. Okay. And let's give our sine wave let's give our sine wave a little bit more amplitude first. Of course, our offset we can put it here. Okay, I'm not going to use this local variable trick again. I'll just use the things as is. Okay, so I have an offset which I can control, baseline heater power. Okay, so this is like the baseline heater power. Maybe we'll just put it in joules per mole. And frequency, well, we can actually sort of let's get a control. Heater oscillation frequency in hertz. And of course the last one we will have is amplitude. Let's make a control here. Heater oscillation amplitude in hertz. And I think now we are more or less ready to test it out. Of course, I expect things to go wrong. At least we have some sort of a system here that describes an Ahemos relationship. Okay, of course, these things I can make into a sub VI. I can make all of this into a sub VI, but I'm not going to do that now. All right, so let's just test things out. And of course, I want another waveform chart here. All right, and that will be something like a heater power. Don't save. Okay, heater power. Okay, and we'll just wire that in. I'll just put this in joules versus time, joules per mole versus time. Okay, don't save. Okay, now we can start. Okay, so remember those three things we wanted to control. One's the heater oscillation frequency, one's the amplitude, one's the baseline power, which we can just put at maybe 50,000. I'm not going to do too much. Okay. Oh, okay. So let's stop this. We have an infinity error kind of thing. So let's see. Now maybe the equation's a little bit stiff. So let's make the step size smaller. Okay, never mind. At least we have a basic structure now. We'll have to debug this and try to make it work. Alright, so no guarantees things will work out nicely, but yeah. This is basically what we want. So we'll spend some time trying to fix this thing, and then we'll do frequency response on it, see what the results are. Then we can analyze it with some Bode plot. Okay, thanks for watching.